So we're going to continue on now after talking briefly about simple harmonic models and oscillators. Chapter 9 in our current textbook discusses polar and vectors, polar coordinates, polar graphs, and then vectors. And this material was covered in quite a bit of detail on recording number 18. So you can look back at that if this material is a little bit unfamiliar to you. Here's the key ingredient that you want to make sure you remember. Remember, we measure angles counterclockwise off the positive x-axis. So positive angle measure could be this way. The angle could be at any location in any of the four quadrants. Remember, though, that the point out here on the end is located in our convenient rectangular coordinates x, y, but we also have polar coordinates, oftentimes written as r comma theta, as polar coordinates. And there's a relationship between the four items that you see here, x, y, and r and theta. So if you want to translate something from rectangular into polar form, all you have to remember is this picture and the relationships that exist in that picture. So if you know the xy and you want to turn it into r theta to be able to describe that location, then x right here is the adjacent side next to theta, next to the angle theta here, and r is your hypotenuse, can be thought of that way. So what you observe here, and this is discussed, like I said, in more detail back in recording 18, but if you had your unit circle, I'll just make mention of this, you should be really good with that. This leg down here, the horizontal leg, is your cosine of the angle theta, and with a hypotenuse of 1, and the height right of the end point here is the sine of angle theta. And if you just scale that thing to some other value instead of 1, like larger for r or smaller for r, then you just scale all three of these sides. Easy for you to remember it that way. And so therefore x is equal to r cosine of angle theta. Another way of explaining that is that just look at what the definition of cosine of this angle theta is here. It's x over r. X over r is cosine theta, so just multiply both sides by r and you get this expression. Similarly, if you scale that, y becomes just r times the sine of theta. So that's how you translate from, this is actually going to go the other way, I'm sorry. If you knew r and theta, you'd just put your values in here and you'd then be able to create the x and y readings. So what I just did was actually backwards to what I described there. This is going from knowing polar information and translating it into rectangular. All right. If you're going to go the other way, if you know x and y, and you're trying to move it into the polar form and figure out what r and theta happen to be, look at the relationship to be able to find r here if you know x and y. It's just your Pythagorean relationship. So r is going to be the square root of x squared plus y squared. And also, if you know x and y, you can find angle theta because you know that the tangent of angle theta is given to you as y over x. And then you'd take the inverse tangent here of y over x, and that's going to give you your angle at which that point lies. Keep in mind here, folks, that you have to use your brain on this, because if a point is described somewhere other than sitting right here in this first quadrant, like if it's over in the second quadrant or third quadrant, then you have to be very careful on, say, using a calculator to just punch this inverse tangent. So always draw the sketch, which you've heard me say before repeatedly. Always draw the picture. Now let's see, I think I can illustrate that with an example or two I picked out. Illustrating that concept right there, I didn't have anything written down, but let's just do it. Let's say I happen to give you a point in XY format, rectangular format, that happens to be located at -3, 4. And I want to know the polar coordinates. So what I'm going to do is I'm going to draw that picture, and I'm going to go to -3 and up 4. And here is the R, and that point is located right there in rectangular form. I want to know this angle and be able to find that R value. And I can see that I have a 4 reading right here and a -3 right there. And you can see that the R value then is going to be the square root of -3 squared plus 4 squared. 9 and 16 is 25, so R is equal to 5. A classic textbook problem where the legs are 3 and 4, the hypotenuse is 5. The angle, however, is a little more exciting. Take the inverse tangent of your Y reading, 4, over your -3. Now what's going to happen if you go back and review the material on inverse trig functions, the inverse tangent only exists for quadrants 1 or quadrant 4 angles. So what the calculator is going to come back and tell you is it's going to come back and tell you this negative angle reading right here. We'll do that on the calculator in just a second. So what we're going to have to do with that negative angle reading is we're going to have to add 180 degrees to it to get it over here into the second quadrant. So if I'm in degree mode with my calculator, and then I add to this 180 degrees, this is where the brain comes in, I'm going to end up with a proper angle sitting over here in the second quadrant. So let's punch that on the calculator quickly. So we punch inverse tangent of 4 divided by -3, and then I make sure I have to add 180 to it. And there we are. Oops, that doesn't look right. Does that look like it's close to 180 degrees on the picture? Heck no. So look what's wrong. I come back here, my calculator was in radian mode. I should be in degree mode for this calculation. So I quit, I make sure I'm in degree mode, come back to the home screen, hit enter again. Ah, that feels much better. So you have to always keep your brain engaged there, and you can see that theta then is about equal to the 126.9 degrees. So that's how you then come up with those coordinates, 5, 126.9 degrees. Now there's a lot more discussion we could do about polar coordinates. This point in polar could be described with positive or negative R. We could have the R value as negative and have the angle down over here, and you have to go back to tape number 18 to see that information or more detail about that. Here's another polar thing we could do quickly, and then I'm going to have to jump onto some other topics pretty quickly. Let's say I wanted to look at the following. I'm given an equation, R equals, how about 3 over 3 minus cosine theta? And what if the question is, translate this from a polar form into rectangular? Polar form into rectangular. So all you have to have in mind is the definition that we used earlier. So what I would first of all probably do on this problem is clear the fractions. Multiply both sides by this denominator, and I'm going to end up with 3r minus r cosine theta equals 3. If you remember the little triangle back on the previous board, then you know that r is the radical of x squared plus y squared, and you know that r cosine theta is x. So now we have it where it's only involving the variables x and y. We probably could tidy this up a little bit by isolating the radical. Since it's a radical equation, isolate the radical, and so we're going to have 3 times the radical equals x plus 3 by adding x to both sides. Now if we square both sides of this, we're going to end up with 9 times x squared plus 9y squared equals the binomial square on the right, x squared plus 6x plus 9. Review those basics if you need to. And then move the combined like terms, And so we see an 8x squared minus 6x plus 9y squared equals 9. Now this is something that comes up in the next chapter. And it turns out, if you're familiar with that material, in the next chapter on analytic geometry, this is an ellipse. It happens to be an ellipse. And we'll talk about that in a few minutes in the review session. So now, if we come back to our calculator and we take this particular function and we drop it into the calculator in polar form, in polar format, we can actually draw its picture. Can do that kind of quickly here. I have to go to mode. I want to come down, I'm going to leave the calculator in degree measure. I'm going to come down here to mode and come over to polar. And now I'm in polar mode. I come back here to my y equals, and you can see y equals is not y1 anymore, it's now r. And so I'm going to punch that function in here, 3 divided by, and I have to make sure that denominator stays tied in there with the parentheses, and we have 3 minus cosine theta. Use your x key up here, the normal x key you usually use, but now it's theta is your independent variable. And then I want to close that denominator with another parentheses, that second parentheses over here. Now, we have to set a viewing window. We have the control over the graphing. Let's let it go from 0 to, why don't we just say 0 to, say, 180 degrees. And let's let it draw every 5 degrees. And then let's set up a viewing window. I'm just looking at the equation, thinking about how big this thing is going to be. And if you scratch your head and think about it a little bit, I'm going to make a guess. Minus 2, 2, 1, 1.5, 1.5, 1. This is a first guess. Oops, then I need to have a negative 1.5 here. Insert negative. And this is a first pass guessing this window settings. Not very wide and not very tall. Oh, it stopped on us. Darn. Well, look back at your window. I only let it roll to 180 degrees, and did you see how it drew that? Let's let it go to 360 now. I'm pausing it. In polar form, right now, we're sitting here probably about 50 degrees or so, that point, and the r value is this distance from the pole. And then that thing's going to continue to go. There it is. It's an ellipse, a distorted circle, and we talk more about that in a little later in the review session. So that gives you an idea of how to handle that. Go back and review tape number 18 for the polar coordinate material. And then I want to now talk about 9.2, which are polar equations and graphs, which is really what I was just doing here. 9.2, polar equations and graphs. And this previous problem right here, this equation does not lend itself real nicely for me to hand graph this. So oftentimes, though, the equations lend themselves more simply to being able to hand graph the polar shape. So here's an example, and this material is talked about in number 8, recording 18 and number 19. So here's an example. What if r is a little simpler? What if it's minus 2 sine of theta plus 2? We could draw what I like to call a rectangular plot, just like you did back in the beginning part of trigonometry. This is going to be an upside down sine wave that is lifted, amplified by a multiplier of 2, and is then lifted up by 2. So I'm going to have an axis that's going to be up here at 2, at an r value of 2, and it's going to oscillate upside down. It's a sine wave, it has an amplitude of 2. So it's going to come down, come back up onto the axis, rise to 4, back to 2, back to 0, and continue on in that fashion. Its period is, right here, a normal 2 pi. Or, let me go ahead and keep it in degree measure. If we keep it in degree measure, this would be 360 degrees. This would be 180 degrees, and this would be 90 degrees right there, and 270 right here. All right. I have to admit, this is a little strange giving a recording session without students' interaction. So anyway, the intent here is to give you a quick summary of some of this material so that you can then use it if you're taking calculus or doing a quick review in trigonometry. So now, this is what I call a rectangular plot. What we're interested in is taking this equation and not just using our calculator to generate the graph, but we want to generate the polar plot, or polar graph. So now we're coming off the pole and we're measuring R values as we let theta change from 0 degrees to 90 degrees to 180 to 270 to 360 and any other angle in between. So look what's happening to the radius from this graph. The radius is starting here at 2 when we're at 0 degrees. So I'm at 0 degrees, I go out there a distance of 2. I'm not going to go quite that far because the scaling here. Go that far. So there's that first point right here. This point corresponds to that location on the polar graph. Then, as you move to 90 degrees, look what's happening to the radius. The radius is shrinking to 0. So as we move towards 90 degrees with these angles, the radius is coming in towards 0. And then, as you go past 90 degrees, the radius is starting to grow again, similarly to the way that it decayed in the first 90 degrees, starting to grow symmetrically. And you can see a symmetry line right there at 90 degrees. You can see another one over at 270. And what's going to happen on your polar graph, you're going to see symmetry on the polar graph that matches the symmetry you see here. So now, look what happens as you move past 90 degrees, heading towards 180. The radiuses are growing the same way that they decreased as you went towards 90 degrees. Watch my finger. The radiuses are decreasing as the angle changes, and it comes back to the pole here. So then, what's going to happen then as we head towards 180 degrees, those radiuses are going to grow, and it's going to grow back out here to 2. So at 180 degrees, we have a radius of 2. So here's where that point plots. Let me put a triangle on that one. A triangle right there. Then we keep on going. Look what happens after 180 degrees. The radiuses are getting larger and larger and larger until they become a value of 4 when you get to 270. So when you're pointing downward, the r-axis points downward, then you're going to plot 4 out that direction. Right down here, 4 at 270 degrees, and the radius is growing as you move that direction, and what you're going to end up with is this. And then as you move past 270 to 360, the radiuses will come back to that value 2 again, and you end up with a heart. It's not Valentine's Day, but that's called a cardioid. Cardioid. There we go. It's a cardioid. Now watch what happens what would happen if I took this equation and simply lowered it down a little bit. If I just lowered this graph down a little bit, I'm going to get some negative R values in there. And I could do that by hand, but just in the interest of time, let me just kick it into the calculator. And so if I take in polar still, and I take this equation, -2 sine theta, and I add, say, just 1 instead of 2 there, then it's going to end up having a little bit of negative R in there. And let's set a window now. Let's set a window that'll capture the kind of shape that we just drew. So on X, say -3 to 3, 1. and vertically maybe negative 5 to 2, 1. And then we will square up this picture because of the distortion created by those strange window settings after we get the picture. And then if I go to then zoom on the zoom command, and I look down here and pick square, number 5, it'll draw this in an undistorted form. And so what happens is it still has a little bit of a wing up here that's a little bit above. Let me refine the window and not go so high. Let me just go as high as, and not quite as low. So I'm going to tighten it up vertically a little bit. Say negative 3. Whoops, I better, yeah, negative 3 I think will be adequate. And then how about 0.5 on the vertical? 0.5, I meant to have it there. Now you can see a little bit. That's called a limison with an inner loop, And that occurred because of the negative R values that were showing up. So the equation on there was, you saw it on the computer. We just slightly altered the original equation. Okay, that takes care of that section. Let's go ahead and do another section of the book now. Let's briefly look at vectors. In 9.4, is vectors, and these would be recording numbers 19, 20, and 21. Part of 21, I believe. And so here's the idea. If we have something called a vector has to have both magnitude and direction associated with it. More detail on these 3 recordings. If I write a vector this way with angle brackets 4, negative 3, another way of writing that is 4i hat minus 3j hat. That vector has length called magnitude, and it also graphs. It has length and direction. So it's 4 to the right and negative 3 on y, and it looks like this. So there's a picture of vector v. Now vector v has its magnitude, which is that length right there, and v without the arrowhead on it is equal to the square root of the sum of the squares of the legs, the 4 and the negative 3. And that, you can see, is the square root of 4 squared plus negative 3 squared, and that's again equal to a simple 5. So the magnitude of the vector is 5. Now we can make a unit vector out of this, make that length, instead of 5, we could make it 1. We could make a unit vector out of that. This is very important in engineering and physics. We could make a unit vector, and we use the same symbol. We oftentimes put a little caret symbol over the top of it to mean that it's a unit vector of length 1, and it's easy to do. All you do is take the original vector and you divide it by the magnitude, and that's going to scale this thing down so it has a length of 1. So it's a little short vector, same direction, so there's a picture of v hat. Is the way I oftentimes say it. And so it's going to be the original vector 4, negative 3 divided by 5, and you can take that scalar value and move it inside to the different elements, components of the vector, and so we end up with a 4/5 comma negative 3/5. Those terms happen to be called direction cosines. And you have to go a little further in math to understand why we call them that. And you'll do that in calculus. Anything else on this? Let's say I gave you another vector, w, and let's say I made that one negative 2 comma, let's use different numbers comma 6. And let's say I wanted to find out the addition or the subtraction of one vector and the other. What if I wanted vector v minus vector w? Then all I do is I just do the math. And so I would have 4, negative 3, and I'm going to be subtracting from it negative 2, comma 6. And your rules of distribution and so forth carry on into the elements here. So what you're going to do is combine the x-directed elements together. So it's 4 plus 2 is 6, and negative 3 minus 6 is negative 9. Negative 9. And we could draw that result, we could draw that picture by drawing both v, which was, we originally had it, 4, negative 3, look like this. Here's v. And then w, the original w, is negative 2, 6, looking something like this. Here's w. Negative 2, 6. So what we're going to do is we're going to take the negative of w, turn it around and point it the other direction, and we're then going to hook it on to v. So it's v plus the negative of w. So we're going to take the w vector and draw it down here, and that's the negative of w right there. And the addition of those is a vector that has this x leg right here, which is 6, and this y leg, which is minus 9, shown right here. That vector is this vector right here, coming from here. There it is right there. That is the vector v minus w. Okay, so that's a very quick little summary of this material on vectors. There are some other important topics in all pre-calculus books related to vectors, and in our textbook in 9.5 and 9.6, dot products and cross products are very important, and they're talked about in those two sections, which we did not cover in this course. So I think that'll go ahead and end this segment on polar and vectors, and then we'll go on to analytic geometry here in just a moment.